Hello, and welcome to this short course on models of social dynamics. My name is Paul Smaldino. I'm an assistant professor of cognitive and information sciences at the University of California, Merced, and I am looking forward to going with you on this journey into modeling. All right, we're here because we're interested in understanding the complex dynamics of social, ecological, and evolutionary systems. This is inherently challenging. One reason that it's challenging is because the tools used to describe those systems, especially for those trained primarily in the social sciences, tend to have severe limitations. We use verbal models mostly, and these are great. They can paint vivid pictures in our minds, but they're often ambiguous. We use statistical models, which are important for establishing empirical relationships or some association between variables, but they rarely establish causal origins or mechanisms for phenomena that we're interested in. So this course is about formal models, mathematical and computational models of complex processes. More specifically, in this module, we'll focus on relatively simple computational models that even those without heavy math or programming backgrounds should be able to get off the ground relatively painlessly. Formal models can help us communicate ideas unambiguously, and they provide us with a toolkit with which we're better able to form intuitions and to develop generative theories about the behavior of complex social systems. So, the material for this course is inherently interdisciplinary, and we're going to cover models on 5 topics that should be of interest to almost anyone who studies social behavior. After this introductory unit, each of the next 5 units will focus on a broad topic and some simple but illuminating models. So we'll deal with contagion, opinions and polarization, cooperation, coordination and norms, and sociopolitical cycles. Before we get started, I want to go into a little more detail about what models are and how they're useful. After that, before the unit's over, I'll give a brief introduction to the NetLogo programming language and how we'll use it to explore agent-based models. So, what are models and how should we use them? So, models are structures, which can be abstract or physical, that can potentially represent real-world phenomena. Lots of researchers use models. How do you know if you're using a model? Well, you can ask yourself this question. Am I directly studying the thing I'm interested in? Sometimes the answer is yes. If I want to know the mass of a rock, I can weigh the rock. Not using a model, I'm studying the thing itself. Very often the answer is no. However, instead I represent my system of interest with something else. In this case, you may be using a model, which is any structure that represents some other real-world phenomenon. So engineers may use physical scale models to assess design principles. So this is a scale model of the San Francisco Bay watershed. You can visit this. It's a giant model in Sausalito, California. Biomedical biomedical researchers may use animal models to make general inferences about genetics, hormones, behavior, etc. Behavioral or psychological researchers may design experiments that model the larger class of phenomena of interest. So consider the famous marshmallow test depicted here. Unless you work in the marshmallow industry, you're probably not that interested in how long children can wait to get a second marshmallow before eating the first. Instead, researchers use this scenario to model situations where issues like willpower and trust and authority come into play. And finally, we can build formal mathematical and computational models. Sometimes these models are extremely specific and are basically simulations of physical models used by engineers. And sometimes the models are more abstract and instead are designed to capture core elements of a theoretical idea. Formal models are special because they contain nothing more or less than what we put into them. Sometimes critics say, well, you baked some result into the model, so it had to happen. And on some level, this is literally true of every formal model, because the model is merely a series of computations specified by the modeler. But to put it another way, a formal model is a logical engine that turns assumptions into conclusions. This is useful because our intuitions about complex systems are often terrible. Good models can often show us how our assumptions lead to conclusions, sometimes unexpected conclusions. Models can do a bunch of things for us. We use models for a lot of reasons, and here are some. Prediction. Sometimes models let us make empirical predictions. This is obviously useful, but models have lots of other uses besides prediction. Precision. Well, the world is messy. Words are ambiguous. We can often speak past each other. Even sometimes using the same words, we can mean different things by them. Multiple individuals use the same words in different ways, leading to several interpretations that are consistent with the same sets of words, but may lead to different conclusions when interpreted. In contrast, a formal model is specified in math or code and is very clear on what it does or does not do. Tractability. The world is complicated. Data may be hard to acquire due to constraints of time, space, or cache. And if we're interested in big picture stuff like history or evolution, we can only run the clock once. Models, on the other hand, are only constrained by our ability to imagine how a formal system might be constructed, and to some extent by the limitations imposed by what is computationally feasible. Finally, of the ones I'll talk about, mental models. Right? Formal models give us mental models. How we interpret what we see in the world is shaped by our ability to draw analogies to things we have experienced or imagined in the past. Everything we learn is filtered through the narratives we hold in our memory. So, by learning about formal models, we arm ourselves with new analogies for the behavior of complex systems. Of all the uses for formal models, it's contentious, but this may in fact be the most powerful. I want to talk briefly about hypothesis formation and what is sometimes called the articulation of parts. In order to form a hypothesis or a theory about some system, we have to articulate the system in terms of a set of parts and the relationships between those parts. This is sometimes called decomposition of the system. How should a system be decomposed? There's no one right all-purpose answer, but instead we have to shape this decomposition by what is useful for constructing a meaningful explanation. So to go into a little more detail about this, I'll look at two prominent classic examples of models. So let's start with one of the seminal models of modern science, Newton's model of gravity. So in the early 17th century, Johannes Kepler used the best available astronomical data to show that not only did the planets orbit the sun and not the Earth, but that their orbits were elliptical and not circular. Why? No one knew. In these early days of Western science, several explanations were proposed, but it was Isaac Newton, the giant weirdo of Cambridge, whose explanation persisted because he developed it using a formal model. So Newton proposed a universal law of gravitation in which objects are attracted to one another with a force proportional to their mass and the inverse square of their distance. What's really noteworthy, if you look into the history of this, is that others besides Newton had also proposed that the force of gravity might be approximated by an inverse square law, including sort of luminaries of the early days of science like Robert Hooke, Christopher Wren, and Edmund Halley. Newton, however, was the first to test the consequences of this claim. By modeling the trajectory of one celestial object around another, he showed that an inverse square law could give rise to the observed elliptical orbits, and this enabled his theory of gravity to remain the gold standard for over 200 years. Let's take another example, this time from ecology. For decades, fur traders like the Hudsons Bay Company in Canada noticed cyclical patterns in the populations of the animals they hunted and used their fur for trading, like the Canada lynx and the snowshoe hare. Seen here, this is the real data collected by the Hudsons Bay Company from 1845 to 1935. Not only did the populations rise and fall, but their cycles seemed to be locked in phase and unexplained by external factors like climate. An explanation came from two Italian mathematicians working separately in the 1920s, and they applied ideas of autocatalytic chemical reactions to the problem. Assume that, in the absence of links, hairs will reproduce and increase in number. In the absence of hair, links will starve and decrease in number. When both are present, and here's where it gets interesting, links will eat hair, increasing their numbers while diminishing the hair, their food source. When these assumptions are formalized, which can be done using coupled differential equations, the cyclical patterns observed by the fur traders emerge. This is data from numerical simulations of the model. But both of these examples concern models being used to explain existing patterns in data. As we'll see, models can also be used to explore more abstract theoretical ideas, though in such cases more background is usually needed, which we'll get to. Both of the examples also are expressed as mathematical equations. In the Lac-Volterra model, the populations of predators and prey animals are each expressed as a single number. This has a nice advantage of tractability. We can often find exact solutions, but it also has a few disadvantages. One is limited realism. So models, mathematical models assume a lot of homogeneity to make them tractable. All the links are exactly identical. All the hair are exactly identical. Most social populations have important sources of heterogeneity that we might not want to ignore. Another limitation is the degree to which results are intuitive. If you don't have deep mathematical training, equations often provide limited insight. And finally, mathematical modeling has a relatively high bar to entry. You have to know how to do that kind of math. And lack of mathematical training can prevent access to models that are valuable. And especially, at least the current state of the social sciences don't require the kinds of advanced mathematical training that is often necessary to understand mathematical modeling. So luckily, there is another way, which is agent-based modeling. Here's a few examples. So an agent-based model is a class of formal model in which individuals, aka agents, are simulated as explicit computational entities. So for example, instead of using a single number to represent all of the predators in a population, we would represent every single predator as an individual agent. So there are some costs to using agent-based models. In case, instead of clear analytical results, we have to run simulations and often rely on abductive reasoning to draw conclusions. There's also a lot of benefits, though. Agent-based models can account for more heterogeneity, more complexity, more population structure, and generally have a lower bar to entry. It's usually easier to teach people to code than it is to teach them how to analyze differential equations. The trade-off of what approach to use you should use is relative to the research questions being asked and also the sort of competence and comfort level of the researchers. I want to be clear, though, that I think it's counterproductive to debate whether mathematical or agent-based models are better. They're both useful. Which one is appropriate for you depends on the complexity of the problem and skill set of the researcher. In many cases, we can try to get as far as possible with mathematical analyses and then tackle the more complicated questions with agent-based simulation models. On the other hand, agent-based models might be more intuitive and easier to implement than mathematical models for many scholars. And for that reason, in this course, which is designed to be an introductory course on modeling, we're going to focus on agent-based modeling. So, agent-based models are explicitly computational. You will therefore have to write your model using a computer language. Most programming languages are Turing complete, which means that in theory, anything you do in one language, you can do in any other. I have personally worked on agent-based models in Java, R, MATLAB, Python, and NetLogo, and I have colleagues who regularly use C++, JavaScript, or Julia. I even saw one published model using Excel Please don't do this. It's a terrible choice, and you'll regret it for as long as there is a you to regret. Okay, in general, you should use whichever language you're most comfortable with. For this course, we need to pick a language, and we're going to use NetLogo. Dun, 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 dun. NetLogo first appeared in 1999 and is a software package expressly designed to build and analyze agent-based models with the philosophy of low threshold, no limit. So low threshold means that NetLogo is pretty easy to learn even for those without previous coding experience. It has a bunch of drag and drop features and many built-in functions common to models of social behavior. No limit means that, in theory, NetLogo can be used for high-level scientific modeling. And many peer-reviewed papers are published every year using models built and analyzed in NetLogo. For me, the primary reason to use NetLogo for this course is that it is designed to be easier to learn with syntax that reads like pseudocode, and it is extremely easy and fast to get dynamic visualization and plotting. In general, I think it's a really fun program to play with, and I hope you agree. So this class assumes no prior knowledge of programming, but some exposure with the basics, things like variables, conditional statements, and loops will be helpful. Even better if you know something about object-oriented programming, but it's okay if you don't. So what I am not going to do is give a detailed course on how to use NetLogo. For this, I strongly urge you to download NetLogo and go through the tutorials that are included in the user manual. Also, a great thing to do is play around with the code that are included in the models library, and I think you'll get the hang of it fairly quickly. This has been the experience of a lot of people I've talked to. And you can find all necessary materials at the URL listed. NetLogo is free and open source, so go at it. Let's talk origins for a second, because I like the history of science. So the most basic unit of an agent-based model in NetLogo is called a turtle. And there's a reason for this. Most times the turtles are your agents. Why are they called turtles? Well, in the 1950s, a scientist named Gray Walter made a little simple robot that could be easily programmed to walk around the room by accepting commands for distance to walk forward and for what angle to turn. He called this robot the tortoise, just because it kind of vaguely looked like one. So inspired by this, in the 1960s, a group at MIT, Ferzig, Papert, and Solomon, introduced the Logo programming language, in which a little green turtle can move around similarly, allowing users to draw different shapes. I remember playing with the NetLogo language when I was in elementary school in the late 1980s. So this little triangle was called the turtle, in part in honor of Gray Walter, and in part because that little green triangle sort of looks like a turtle if you kind of squint. NetLogo follows in this tradition. It gets its name because it uses networked turtles. So turtles are objects that are located in space, can move, die, and reproduce, can be networked, and can have any number of properties you want to give them. The space they're on are patches. So the default space in NetLogo is a two-dimensional grid of square patches. Patches are defined by their location and do not move, but they can have arbitrary properties as many as you want to give them. They can interact with the turtles, and some models will use patches rather than turtles as the principal agents. NetLogo also has a third category of object called links, which can be used to model arbitrary network structures. We're not going to deal with these in this course, but it's a really nice feature for network models. Asking. So one of the most important things needed for an agent-based model is the ability to command each agent to execute the same set of commands in a random order on each tick of the model's clock. In NetLogo, however, we don't command, we ask. NetLogo is a very polite language. So of all the procedures used, the most important one is ask, which generates a list of all the agents that meet some criteria, and in a random order has each of them run some block of code. So here is a procedure called move, and this is the NetLogo code which defines this procedure. And when move is called, it asks all the turtles, and so each turtle in the simulation will, in a random order, first turn left a random number between 0 and the variable turning angle, then turn right a random number of degrees between 0 and the turning angle, and then move forward some amount defined by the variable speed. So this move procedure generates a correlated random walk. Finally, or at least of the components I'll talk about in this part, there's something called behavior space. I'm not going to go into this in too much detail, but NetLogo has this really useful tool for doing batch runs to get the distribution of model outcomes over a range of parameters. So the purpose of this tutorial, this course, is to introduce insights from modeling. It's not a course on how to analyze models, but any data I show that aggregates data from across many simulations, I use behavior space to generate those data. So batch runs are essential for analyzing agent-based models. I will talk briefly about model analysis in the very last unit. If you're going to use NetLogo for agent-based modeling, behavior space is pretty much an essential tool. So let's look briefly at a very simple model, or a simple simulation. So in the provided code for this course, you'll find a file called movement.nlogo. So go ahead and open that. And this is what it looks like right here. It has two buttons. If I go to edit the buttons and look what it does, this is just the button executes the command setup. These are sliders, which control the variables num_turtles, which is the number of turtles, speed, turning angle, and then there's a Boolean switch for a variable called pen down, which on just sets it to pen down to true, off sets pen down to false. And so the point of this is to get familiar with coding of a model. And I'm going to create a simple simulation that creates some agents and has them move around. This allows us to get familiar with some of the methods and conventions of NetLogo and agent-based modeling. In this unit, and in every unit in this course, I have provided the basic model code so that we can focus on understanding the model's behavior. So at your own pace, you can examine the code to understand how it works and how the assumptions of the model were translated into that code. So in this first simulation, which is not really a model of anything, we're going to create a bunch of turtles and have them execute a simple correlated random walk. For fun, we're also going to enable them to leave colored trails of their movement paths. So our model is going to have several parameters that we can manipulate on the fly, which are these switches. So num_turtles is going to be how many turtles are in our simulation. Speed is going to be how fast the agents move, but which really will be how large a step they make at each time step. And turning angle will be the maximum angle that they will turn on a given move. So our agents are going to move around in a two-dimensional space, which is this big black square here. And it has toroidal boundaries, which are also called periodic boundaries. That just means that we avoid the complications of dealing with boundaries and corners in our world and allow it to wrap around so that an agent that goes off the left edge of the screen reappears on the right edge and so on. Okay, let's look at the code. So NetLogo models have three tabs: interface, which is this; info, which I have blank, which is a template that allows detailed description of the model; and then the code. This is the entirety of the code for this little model right here. Comments are made using semicolons. It has two procedures, one called setup, one called go. In setup, first, use clear all to clear all the variables from memory, and it creates some number of turtles. Determine how many is determined by the variable num_turtles. Each turtle that's created executes this block of commands. It sets its shape to a circle. Default is an arrow, and it sets its XY position to be some random location in the space, and then reset ticks resets the simulation clock. Pretty much every model we're going to look at has a setup procedure that begins with clear all and ends with reset ticks. So if we go back to our interface, make, let's say, 5 turtles and set them up. There we go, there's 5, and they're randomly colored, but they're all circles. I can set them again, and I get 5 more different colors, different locations. What happens when I go? So let me go back to the interface for a second. Notice that Go has these little arrows, these circular arrows here. That's because if I edit it, I've clicked forever. And that just means that once it runs the procedure, it runs it again and again and again and again forever until some stopping condition is met or until I click the button again. So what happens? So let's ignore this first part to start and get to the second part. What happens is I ask turtles to turn left, then turn right, then go forward. So we saw this already. So random is a procedure that's baked into NetLogo, and it generates a random integer between 0 and whatever you give it. So it's going to be greater than or equal to 0 and strictly less than turning angle. So the larger turning angle is, the wider the range of possibilities. And then it moves forward one step, some number of spaces determined by speed, and speed can be a fraction, where here forward 1 is the width of a patch. So I'm going to make this really simple and just make 1 turtle. Click go. So I actually wanted to. Let's start pen down. Yeah, it's very difficult to see, kind of jumping around. What I can do is slow it down quite a bit. You see it kind of darting around the screen. It's a little hard to follow. If I make the turning angle very small, then it's going very quickly and moving almost in a straight line. And that makes sense. If I make the turning angle really high, it kind of jitters. I've added this feature called pen down. I turn it on. Now we get this nice trajectory where it draws basically, it leaves a trail wherever it goes. So we can see how the random walk changes from where I have it pretty small. The turning angle is very large, so it's very tight random walk. To make the turning angle smaller, it's moving more forward and it explores the space in a more exploratory fashion. So if I go back to the code, you can see how I did this, where I created this if-else statement. So if-else pen down. And the question mark is just part of the variable name, and just NetLogo has a convention where Boolean variables end with a question mark, which is just treated like any character. You don't technically have to use the question mark, but it's just a nice way of knowing that you're dealing with a Boolean variable. And so an if-else statement then takes 2 blocks of code in brackets. The first one is executed if this thing is true. The second block is executed if this thing is false. And so if pen down, then ask turtles. So it tells all the turtles, put your pen down. Pen down is a built-in command. And otherwise, ask the turtles to put your pen back up. And we can make cool kind of, abstract art by making, let's say, a bunch of turtles having their pen down, taking a little longer, a little more time to run. Let's go a little faster. Yep. And now we can make pretty pictures, kind of janky Jackson Pollock. Okay, that's it. Play around with this model, take a look at how it works. I recommend also you can just see what you can do with it and try to get it to do different things for fun. So let's talk about how the rest of the course is going to work. So what we just did, this was our introduction. Including this one, the course is divided into 7 units. Units 2 through 6 will each focus on a particular class of models, and the short Unit 7 will summarize the lessons learned and suggest directions for further study. So In Unit 2, we'll consider models of contagion, diseases, behaviors, or information, how diseases, behaviors, or information can spread from one person to another. In Unit 3, we'll look at opinions, modeling information in a slightly more nuanced way as a continuous rather than binary variable, influenced by social forces and individual predilections. In Unit 4, we'll consider a key factor in social organization, cooperation. We'll look at this through the lens of an evolutionary game theory perspective and see how cooperative strategies might be able to overcome those strategies that could exploit their goodwill. In Unit 5, we'll consider that cooperation works best when individuals can coordinate on norms and goals, and we'll investigate how new norms might spread. And Unit 6, we'll consider dynamics that are cyclical rather than those that converge to equilibria. We'll first tackle a simple predator-prey model before turning to a more complex model about the rise and fall of empires. Finally, in Unit 7, we'll consider what we've learned and how we can apply it moving forward. I've chosen these topics because I think they're foundational to understanding social change and cultural evolution. For me, a useful mnemonic for these foundations is the 3 C's: communication, cooperation, and coordination. Understand these, and you understand a lot about human nature. At the end of each unit, I'll also talk about how the ideas and the models I presented have been extended and taken in other directions by different researchers. So let's get started. Thanks for watching.